Hello everyone. Hope the past session on theory of equation, session 1, the fundamental theorem of algebra and its application of theory of equations, you have understood. Now this is the time to find the location of roots. You have to find the roots and its location for polynomial equations. Theory of equations we will basically do for algebraic equations, because I told you earlier this is going to be continuation of polynomials only. Polynomial compared to 0, then it will be a polynomial equation or algebraic equation. Today's class we will be learning, some of you can say it is relearning, because intermediate value theorem you might have learned in continuity, those who are in class 12. Rolle's theorem you might have done. Descartes rules of signs not done, that I will explain in details. Multiple roots of polynomials, little bit idea you have got in polynomial session 2 or 3, I don't remember it exactly. You can go through my past videos on polynomials to get the idea of multiple root. But today's class I will be discussing again and will show you the application of these beautiful theorems in solving algebraic equations or predicting roots of algebraic equations. You know, polynomial equations are always continuous. Graphing is possible always. If the graph of polynomial intersects the x-axis, the point where it intersects, it is going to be a root of the equation or 0 of the polynomial, isn't it? 0 of polynomial and root of polynomial equations are synonym, but we use in different purpose. When only polynomial is there, we say zeros of polynomial. When equation is there, we say root of the polynomial. Root of the polynomial, zeros of polynomial, whatever you say, when you plot the graph will be intersecting at the points on the axis where there is a root. If it intersects at 2, 3 and 4, then x equal to 2, x equal to 3 and x equal to 4 are 3 roots of polynomial equation. Should keep this concept in your mind. So when you are going to state about the theorems you need for finding roots and locations of polynomial equations, first in your mind intermediate value theorem should come. It's a very interesting theorem. If you have done in continuity, it's fine. Try to understand with me here again in case of polynomial equation. Suppose a polynomial, when you plot the graph of the polynomial, it is intersecting the axis at these points. Okay, as I told you, these are roots of the polynomial. Polynomial y equal to fx. Now, at the extreme point or any point before it, no problem, you just draw a perpendicular on x-axis. And from this extreme point also you draw a perpendicular. Okay, these are perpendiculars on the axis. Now, if these 2 points, their x coordinate be alpha and this one is beta, this is your x-axis, then you can say that there are 3 roots in between alpha and beta. What are those 3 roots? The root is at a, let it be a comma 0, this is b comma 0, this is c comma 0. But what is the value of f alpha? This is less than 0. What is the value of f beta? This is greater than 0. Okay? Now, f alpha and f beta, they are of opposite sign. You can see that f alpha less than 0 and f beta greater than 0. That alpha and beta, you can take alpha less than beta, beta less than alpha, it doesn't matter. But one thing clear, if there is a root between these 2 points, then f alpha into f beta, their product should be less than 0. Can there be only one root possible? Yes, one root also can be there, just one root. See, if this one beta, this one alpha, then there is a root at this point between alpha and beta. So, what's intermediate theorem all about? It states that between 2 points alpha and beta, if the graph crosses the x-axis, there will be root at that point where it crosses. But provided the value of f alpha and f beta must be opposite signs. So if f alpha and f beta are of opposite signs, there exists at least one root. There may be 3 roots, and also there may be more than 3 roots. If you draw the polynomial graph, see, how many roots are there? This point is alpha this time. This is alpha. This is beta. So, how many roots are there? 1, 2, 3, 4, 5. Okay? So, between these 2 points, alpha and beta, as they are of opposite sign, as this condition is maintained, we can say that there are 5 zeros of the polynomial, 5 roots of the algebraic equation or polynomial equations. So now can't I state the general statement of the intermediate value theorem? What is that? That is, if f alpha and f beta are of opposite sign, then there exists at least one root such that fc equal to 0 as polynomial continuous differentiable, that I told you. But one thing I did not write here, at least one root means how many? If they are of opposite signs, then number of roots will be odd. In this case, number of roots must be odd. Am I clear? 1 or 3 or 5. More than that also possible. So, be sure that if f alpha and f beta are of opposite signs, then there exists odd number of roots, odd number of roots between 2 points alpha and beta. Let us apply it in solving few simple sums, so that the polynomial has a real root between alpha and beta. How to check? There is a real root between 1 and 2. Alpha is 1 and beta is 2 here. So this one you find f1. f1 is 1 cube minus 1 minus 2. This is minus 2, less than 0. And f2 is what? 2 cube minus 2 minus 2. 8 minus 4, that is 4 greater than 0. So f1 and f2 are of opposite signs. As f1, f2 less than 0, Therefore, there is a real root. There is a real root. Maybe all three are real roots. Maybe. But the question is there is a real root. Therefore, fx equal to 0 has at least one real root between 1 and 2. So this concept you should keep in your mind. Right now I am telling 1. Later on in Descartes Rules of Signs, I will see that it may be 3 also. But how? Wait for that. Let us go for this problem. Find an interval of length 0.1 that contains a real root of fx. Is it a bit tricky? No, not at all. You find the sign change, where sign change occurs. See, it's very easy to determine. If you find f0 is what? -1. And then if you find f1, f2 going to be what? 32 minus 3, that is 29. Okay? As they have asked to find interval of length 0.1, this difference is too large. Let me take f1 also. f1 going to be what? This is -1. Since f1 into f2 less than 0, this implies there exists a root between 1 and 2. Okay? There exists a root between 1 and 2. Now go by interval bisection. If it lies between 1 and 2, let us check f1.5. f1.5 is what? 1.5 to the power 5 minus 1.5 minus 1. 1.5 square itself only 2.25. And then if you make it side part, this will be greater than 2.5 definitely. So this is also greater than 0. So there is a root between. Now what have we got? f1 into f1.5 less than 0. Therefore a root must lie between 1 and 1.5. This method later on we'll learn as interval bisection method. But the question is, find an interval of length 0.1. So you check it with f1, f1.1, f1.2, f1.3, f1.5 you already said it is positive. f1.4 you can check. Okay. Now what about f1.1? So let us check this one first. f1 negative, f1.1, this is going to be 1.1 to the power 5, 1.1 minus 1, 1.1 to the power 4. Okay, let me take the help of my calculator once, because it will take long time for calculation only. So this is becoming approximately 0.6105. This is greater than 0. So f1 you have seen negative, f1 negative, and f since f1 into f1.1 less than 0, so there is a root between 1 and 1.1. Go for this one. Prove that the equation has at least 3 real roots. This equation, how to say it has it's a 7th degree polynomial. 7th degree polynomial will be intersecting at how many points? 7 points. If you go by graphing, then you can state that. But here the theorem we have learned, if it is a polynomial of 7 degree, then if you find f0 going to be what? f0 is 1 greater than 0, f1 1 minus 3 plus 1 minus 1 less than 0. So there is a root between 0 and 1, isn't it? f0 positive. What about f of minus 2? F of minus 2 to the power 7, it is definitely less than 0. Okay? So you got a root between minus 2, 0, between 0 and 1. You take another one, f1 negative, you take 2, f2. f2 2 to the power 7 minus 6 plus 1 definitely greater than 0. So you got a sign change. I mean, you got f minus 2 into f0. You see, f minus 2 into f0 negative. f0 into f1, that is negative. And f1 into f2, that is also negative. Can't you see that there is a root between minus 2, 0, 0, 1, 1, 2. Other roots will not find now. You have to wait for the Rolle's theorem, where we can find roots also. Okay, here we can state by intermediate value theorem that there are 3 real roots at least of this equation, maybe all 7, but we will not find it now. Let us go for next one. So that this equation has a root in each of these intervals. Not a difficult one. You just check f of minus 2. Minus 2 to the power 5. So it is minus 32, 10, 1. This is less than 0. f minus 1. f minus 1, it is minus 1 to the power 5 plus 1. This is greater than 0. f0 is 1 and f of 1 minus 5 plus 1 minus 3. And f1 you got minus 3. Let us find f2. 32 minus 10, 22 plus 1, 23. So what have you got for each part between minus 2 minus 1? f of minus 2, f of minus 1 less than 0. f of 0 into f of 1 less than 0. f of 1, f of 2 also less than 0. So this implies that there exists a root in between minus 2 and minus 1, 0 and 1, 1 and 2. Other roots? Not interested to find now. All roots can be determined. Okay, wait for that. This is just the beauty of intermediate value theorem. It will help you to locate the root. At least It lies between which 2 points that you can get from there. Next we are going by this thing, Rolle's theorem, which as a class 12 student you might have done before, but unfortunately this is not included in board syllabus. Now it is. Few years back it was there, now it is not. Just I show you one thing before we start. We are discussing about algebraic equations, okay? When we will do calculus, we will use the same theorem over there. Suppose a polynomial equation graph is like this. You can see that there is a root. There is a root at this point, at A, at B, and at C. Okay? There is a root between A and B. There is a root between B and C. Now, just a little bit imagination. Will you be able to draw a tangent here? Will you be able to draw the tangent to the curve here? Yes, you can do. You can draw the graph here at this point. At this point, G and H, you got graph. But these lines, the tangents you have drawn, they are parallel to x-axis. So if this is y equal to fx, and we see that this point is alpha and this one beta, then there will exist points G and H on the graph where f dash x equal to 0. Here also f dash x equal to 0. Okay? So you got a root between A and B. If this point has coordinate A0, this one B0, this one C0, you got a root at alpha. Whose root? The equation, no, not the given polynomial. It is root of f dash x. We got f dash alpha 0, f dash beta is also 0. Okay? So f dash alpha 0 and f dash beta equal to 0. It means between two successive zeros of the polynomial fx, there exists a 0 of f dash x. Here also between B and C, there is a 0. There is a 0 between B and C. Of what? Of f dash x equal to 0. Okay, this is Rolle's theorem. Between two successive zeros of fx, there is a 0 of f dash x equal to 0. This one I will try to, as this one going to learn the application of this beautiful theorem, let us go for algebraic discussion little bit. Algebraically, can you prove this without graph? Let us see how to prove it. You take the polynomial, let the polynomial fx be x minus a to the power l, x minus b to the power m into phi x. What is the meaning of this? You have seen in polynomial, if it is written this manner, it has multiple root. Maybe l times, maybe m times. Okay? Maybe l minus 1 times, whatever. We assume that fx has repeated roots at x equal to a, at x equal to b. Because if you differentiate, so long you can differentiate, that root will occur. Already discussed. Now, if dash x is what? To find if dash x, we are taking log of two sides. log fx is L x minus a m x minus b plus, okay, wait a minute, I have to take log over there, no? Without log not possible. Take log of first, L log x minus a m log x minus b plus log of phi x. Okay, differentiating 1 by fx into f dash x will be L by x minus a m by x minus b phi dash x by phi x. Okay, so f dash x going to be what? That fx into, take the LCM here, that is x minus a x minus b into phi x. Here it will be L x minus b m x minus a multiplied by phi x plus x minus a x minus b phi dash x. Hope you have understood. Now in this equation, what is fx by phi x? Here there is fx by phi x, use it. So x minus L to the power m, sorry, x minus a to the power L, x minus b to the power m, that x minus a x minus b, and then L x minus b m x minus a phi x plus x minus a phi dash x. Clear? And in the next step, what will happen? So this will go up, x minus a to the power L minus 1, x minus b to the power m minus 1, L x minus b, m x minus a, this multiplied by phi x, x minus a to the power, into phi dash x. Now you let fx equal to this thing. This is f dash x. You take fx equal to L x minus b, m x minus a into phi x plus x minus a x minus b phi dash x. Okay, this whole thing I have taken as fx. Fx is what? When f dash x divided by x minus a to the power L minus 1, x minus b to the power m minus 1, then we have this one as quotient. Am I correct? Obviously, this is not going to be equal to 0. We are going to consider the root of f dash x. We are going to consider what? Root of f dash x or root of fx. Because these are roots of fx. Those are distinct. This occurs L minus 1 times, this occurs m minus 1 times. Those are distinct from the roots of this polynomial. Now this polynomial fx, when you find the value of fa, then this is going to be what? L a minus b phi a, because this part 0 and this part 0. And if b, what do you get? This is going to be m b minus a phi b plus 0. Then what is your observation? This a minus b is negative of b minus a. Therefore, what do you get? fa into fb less than 0. What does this imply? This implies that if dash x depend on this now, fx or if dash x has a root between a and b. What are a and b? A and b are the roots of fx equal to 0. What have we got? Roots of f dash x now. There is a root between a and b. Clear? So now on the number line, if you start plotting the graph between a and b, graph of what? Graph of fx only. Then there is a root of the polynomial f dash x equal to 0. This is the point alpha where you find a root of alpha. We are not plotting the graph of f dash x. It is graph of fx only, and we state that between two consecutive roots of fx there is a root of f dash x equal to 0. Let me verify with one very simple example. You take fx equal to x cube minus 3x. How many roots are there? You can find easily without taking help of any theorem. They are all real roots. We are talking about real roots, not complex roots now. Okay? X into x plus root 3, x minus root 3. So, what do you observe? There are 3 zeros of fx, 0 minus root 3 plus root 3. What about f dash x? This is 3x square minus 3, 3 into x plus 1, x minus 1. Clear? Now, if we start plotting on the x-axis, roots of fx 0 minus root 3 and root 3, and here minus 1 and plus 1. So what do you observe? Between minus root 3 0, there is a root. Between 0 and root 3, there is a root. One more important observation you do, this will help you later. Roots of fx are all real. Roots of f dash x are also all real. Very interesting, very important. Should keep in your mind. Roots of fx, you see, roots are what? 0 minus root 3 plus root 3. They are real. F dash x also has real roots. And roots of f dash x are separated. We are using this language now. Roots of f dash x are separated by roots of fx. You agree or not? These are roots of f dash x. They are separated by the roots of fx. Where are those roots? 1, 2 and 3. Just think once again. Roots of f dash x separated by roots of fx. If I say that roots of fx also separated by roots of f dash x, will you agree with me? You have to. You have to agree with me. Because minus 1 and 1 we have plotted. Here there is minus root 3, there is 0 and root 3. So plot 0 and 1 first, roots of f dash x. And then you get minus root 3, 0, root 3. Got it? So, one very interesting thing we have found, roots of fx separated by f dash x. Roots of f dash x separated by fx. Clear? Let us go for these two important corollaries in this theory of equation. Corollary. Just understood the theorem. Now, application will be found, and then I am stating the corollary. If all the roots of fx, this is f. If all the roots of fx equal to 0 be real and distinct, then all the roots of f dash x equal to 0. There is a proof in the previous sum. They are also real and distinct. And these are different from roots of fx equal to 0. You agree or not with me? They are not matching. They are not matching. Roots of fx equal to 0 are all distinct. Minus root 3, 0, root 3. Roots of, if fx equal to 0, roots are distinct. If dash x equal to 0 also has distinct roots. Clear? Number of real roots of f dash x equal to 0 n minus 1. If you have taken a polynomial of nth degree, then if its number of roots n, then f dash x, and those are real and distinct, then f dash x equal to 0 has n minus 1 roots, real and distinct. You understand? Hope you understand. Okay? And those fx has, say, number of roots 30, f dash x will have roots 29. Okay, I have given you one simple proof with fx taking x cube minus 3x and f dash x this. But later on, we will apply this. This is our corollary 1. Now one thing, in corollary 2 you try to learn that here, between any two conjugative roots of fx equal to 0, between any two conjugative real roots of f dash x equal to 0, there can be one and not more than one real roots of fx equal to 0. How? Just see in the previous example, we got roots minus root 3, 0, root 3. Then we have taken this polynomial, no? X cube minus 3x. I have taken the simplest one. No need to make the thing more complicated here. And f dash x we have calculated, it was 3 x square minus 1. Its roots were minus 1 plus 1. So this one roots of f dash x and those roots of fx minus root 3, 0 and root 3. Between the roots of f dash x, these are roots of f dash x. How many zeros you got? 1. This we can generalize. That between two successive zeros of f dash x equal to 0, there can be one and only one root of fx equal to 0. Okay? Why not 2? Why not 2? Suppose I am taking the general thing here that this is f dash alpha 0, f dash beta equal to 0. And you stated that there is a root. We are saying that two conjugative zeros, no? F dash alpha 0, next f dash beta 0. Maybe f dash gamma 0, but after beta, not in between. These are two conjugative. Alpha and beta are conjugative zeros of are consecutive zeros of f dash x equal to 0. And the corollary states that there will be only one root. Say a for fx equal to 0. Fx equal to 0 has a root a. Now you are assuming that there is a root at b also. Corollary states that there is only one root. You assume that there are two roots a and b. Okay? Now apply Rolle's theorem. Rolle's theorem is applicable for all polynomial equations. These are all real roots and algebraic equation. So between two successive zeros, these are zeros of fx. By Rolle's theorem, you'll be getting a gamma in between a and b where if dash gamma equal to 0. But you stated that gamma will come after beta. This alpha and beta are conjugative. Gamma comes after beta. So what is happening? You stated conjugative roots, but you are getting another root. It's a contradiction, not possible. That's why we can state that there can be only one, not more than one. I have stated again, real root of fx. This is very important. So the basic concept, which is very important, you have understood today. Roots of fx equal to 0 will separate roots of f dash x equal to 0. Roots of fx are all real, then roots of f dash x are real. Between two successive roots of f dash x equal to 0, f dash x, there is only one root of fx. Please keep this concept in your mind. Never forget that. Now, the Rolle's theorem application I have stated here. What are the applications of Rolle's theorem? That already I have told you. To prove that critical points between two roots, the roots of f dash x 0, polynomial of degree n has at most n distinct real roots. Since between any two distinct roots there must be a point where derivative vanishes. If fx is a polynomial of degree n, f dash x will be a polynomial of degree n minus 1. So if fx has n real roots, f dash x has n minus 1 real roots. Okay? Let us see this one. Verify Rolle's theorem for this on 1, 3. So fx is what? Fx is x square minus 4x plus 3. Continuous differentiable, I need not state. Polynomial functions are everywhere continuous, everywhere differentiable. Okay? So, if you are going to apply Rolle's theorem in this interval, we just need to check derivative. F dash x is what? 2x minus 4. 2 into x minus 2. And what do you observe here? f1, 0. 1 minus 4 plus 3 is 0. What about f1 minus 1? That is also 0. f1 minus 1, this is f3, sorry. f3 if you take, this is going to be 3 square minus 12 plus 3. This is again 0. So what have you got there? You got two zeros of fx. What are those? 1 at 1 and 3. Now what have you got? You got a root of f dash x. At which point? At the point x equal to 2, which lies definitely between 1 and 2. And you dare to solve the graph, you dare to plot the graph now. Okay? This technique will help you in future to plot the graph of not only polynomial equation, for all equations. I will be taking a session of curve plotting for class 12 students. I will be discussing all these points over there, and the application of Rolle's theorem I will definitely see. There is tangent parallel to x-axis. There is a root of if dash x equal to 0. Okay? Now, prove that a polynomial of degree n has at most n distinct roots. Already stated, no? Because if a polynomial of degree n is there, their roots are x1, x2, xn, then the derivative, if dash x equal to 0, it is of degree n. They are distinct, x1, x2, xn have taken polynomial fx as roots, x1 or distinct roots. X minus x1, x minus x2, x minus xn, phi x. Phi x is the quotient when you divide the polynomial by this factor. Now, f dash x has degree n minus 1. If this has degree n, f dash x has degree n minus 1. So, roots of that will be x1 dashed, x2 dashed, xn dashed. It cannot go beyond xn because roots of fx equal to 0, they will separate the roots of f dash x equal to 0. And in minus 1 roots you already got. Why do you go out? So it has at most n real roots. If you say that no, one more root is there, xn plus 1, you can assume. Then between two successive zeros there will be a root of f dash x, that is, this is xn minus 1, and this will be xn dashed, another root you are getting. So you are getting a polynomial of degree n minus 1 and getting number of roots n. This is not possible. Contrary to application of fundamental theorem of algebra. So that this equation has exactly 5 real roots. Let us start. Fx will be taking this thing, (4x) f dash x (15x square plus 4) f double dash x is what? 20x cube minus 30x. Why am I doing all these things? This is f dash x we got. We can state the roots now. 10x common, 2x square minus 3. Even you can take 20x common, x minus root 3 by 2, x plus root 3 by 2. See, you are discussing polynomial equations only. In Rolle's theorem, we have stated between two successive zeros of fx, there is a 0 of f dash x. Try to extend. You state between two successive zeros of f dash x equal to 0, because it is a polynomial, there is a root of f double dash x equal to 0. Go for higher derivative. Between two successive zeros of f double dash x equal to 0, there is a root of f triple dash x equal to 0. Understood? So I am just using Rolle's theorem repeatedly. Once you reach this step where you are seeing that real roots are like this, then you start plotting on number line to prove this. It has exactly 5 real roots. Let us go for f double dash x. This is vanishing at 0. This is vanishing at root 3 by 2. This is vanishing at, so this thing 0, this thing 0, this one also 0. These are zeros of f double dash x. Okay? And if that x is a polynomial of degree 4, this one polynomial of degree 3, these three roots of f double dash x separated by roots of f dash x. So there must be, we take this point as a double dashed, b double dashed, c double dashed. Now take 4 roots of f dash x. Since these are all real, this equation of 4th degree must have all real roots. See, you are applying all those concepts we have learned so far. So there is a point A dashed, there is a point B dashed, there is a point C dashed, and there is a point D dashed, where f dashed x will be vanishing. F dashed x is 0 here, f dashed x is 0 here, f dashed x is 0 here, f dashed x is 0 here. Alright? What about f x now? Go back. F dashed x has 4 roots. F dashed x has 4 roots and they are all real. Then roots of fx must be all real. And all these roots of f dash x equal to 0 will be separated by roots of fx equal to 0. Am I correct? So what I am going to do, I am now writing for roots of fx. One root here. One root will be here because between two successive zeros of fx, AB stands for fx and AB, and this part is C, this part is D, this part is E. Why? Because D and E have separated root of f dash x 0. D and C have separated root of f dash x 0. C and B has done it. B and E also has done it. So these are the point where fx going to be 0. 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 This you apply direct for solving ISI CMI MCQ problem. And in descriptive question, if you get the concept, happily you apply the concept, show them. These are the roots of fx, these are the roots of f dash x, these are the roots of f double dash x. Clear? Hope you have understood. Now this one you already have done the concept. Create a polynomial of degree 5 with 6 different real roots. Prove that this is impossible. Just state it. So I am not going to state this one now. You prove it. Take this one as your homework. Okay? Now we are in a position to start Descartes' rules of signs. Descartes' rules of signs. Rolle's theorem, location of roots. Intermediate value theorem, location of roots. In Descartes' rules of signs, you can state location, no. You can state number of real roots. Not exactly. Sometimes you have to predict. Okay? It's very interesting. Descartes' rules of signs states that if we consider sign changes of fx and sign changes of f of minus x, this will give us number of real roots or even number less than that. What is that? If fx, this polynomial signs you write in a row, then observe the signs of those coefficients. How many times signs have been changed? If there is a change of sign, there is a root of fx equal to 0, that is positive root. If there are two sign changes, then positive root will be 2 or 0. If there are 4 sign changes, positive root will be 4 or 2 or 0. What about f of minus x? F of minus x, if you consider its sign, then you can get the idea of negative roots. What is that? F of minus x, you just consider number of sign changes. That number of sign changes will give you number of negative roots. Or even number less than that. If f of minus x has sign change is 1, then negative root 1. That is true for fx also. Only one sign change, one positive root. For f of minus x, same thing. Only one sign change, one real root. Two sign changes, negative root. Two sign changes, either two real roots or number of real roots 0. Three sign changes, it is 3 or 1. 1 must be. Once you are getting odd, then there must be at least one real. Let me clarify with this thing by considering this equation. Go through this again. Number of positive real roots equal to number of sign changes in coefficient. Number of negative real roots, number of sign changes in f of minus x. So, now let us find possible positive and negative roots of this equation. Okay, how to? You just consider signs of fx. Fx signs, x4 has coefficient plus, 0 is there. You cannot write any signs over there, just minus x square. This is plus, this is minus. How many sign changes are there? One sign change here, one sign change here, one sign change here. That is for fx. So what will be your comment? Number of sign changes 3 times, no? Plus to minus, minus to plus, plus to minus. So number of positive roots equal to 3 or 1. What about negative roots? f of minus x, consider its sign changes. You first write f of minus x. f of minus x is what? Minus x to the power 4x4. Same thing. No, this is minus 8x minus 3. So sign changes will be how many? This is plus, minus, minus, minus. Okay? So how many sign changes are there? Just one. So number of negative roots will be what? 1. You cannot reduce. If it is 3, you reduce by 2. If it is 5, reduce by 2 or reduce by 4. Sign change is 5, means what? Number of positive roots will be 5 or 3 or 1. But there is only one sign change. Number of negative real roots will be 1 only. So what have you got here after solving this problem? How many real roots are there? You got 3 or 1 here. We are not sure about those 3 positive roots. Maybe 1 only, but at least 1 positive root is there. And here at least 1 negative root is there. So if you take maximum possibility, these are the possibilities. Maximum positive roots equal to 3, maximum negative roots equal to 1. They are distinct. Positive cannot be equal to negative 1, no. So, if we state maximum number of real roots equal to 4, then it's fine. Maximum number of real roots equal to 4. But we are not sure about those positive roots. Maybe 3 or 1. So we can state that by Descartes rules of sign, we can state that there will be at least 1 positive and 1 negative root. Okay? Maximum number 4, it's fine. But at least one positive, one negative means at least two real roots are there. Okay, let us go for next one. Fx equal to this thing, find possible positive and negative root. What are the signs of fx? Plus, minus, plus, plus, minus. This is for fx. F dash x you find here, f dash, not f dash x, Newton's theorem lag. F of minus x is what? Minus x to the power 5 plus 7x cube 6x square minus x minus 1. So f of minus x sign changes will be how many? Minus, plus, plus, minus, minus. How many sign changes are there? This is 1. This is another 1. Here no sign changes. There is another 1. So number of positive roots equal to 3 or 1. Number of negative roots, how many sign changes? 1. No sign change here. 1. So number of negative roots will be what? 2 or 0. 2 or 0. Number of positive roots 3 or 1. So maximum number of real roots by Descartes rules. Maximum number of real roots 3 plus 2, that is 5, and we can see that at least this is 1 and this is 0. At least 1, this is positive of course, at least 1 real root is there. Now, before we complete this session on basic concept of these three beautiful theorems, I'd like to ask you, after getting number of positive and negative roots, question may be there, find the location of roots. How do you find it? Location of root if you want to find, then you go by intermediate value theorem. See how many sign changes are there in between two given real numbers. You can take 1, 2, you can take minus 1, minus 1. Normally we start with integers, but there is a possibility that there may be between 1.1, 1.2. More specifically, today till this only, I have not discussed anything which is very difficult for you to understand. Hope you have understood, and thank you for staying with me till the end of the session. See you again.